Basically tells us that you have a right triangle with its base x, let's say, and its height h. Now, it tells us that h is a constant. So what that means is that as time changes, this x value can change, right? But the height is going to remain a constant. Okay, the height is going to stay the same. So these two heights are the same. So this could be x1, this could be x2. After some time period, excuse me, so some time period, and then you have this h staying the same. Now, h being a constant means that you really want to treat it like a constant because it's going to make differentiating a lot easier. You're not going to have to write dht. And if you do, if you think of h as not a constant, and then remember, if h is a constant, how is a constant changing with respect to time? 0, always. So you could differentiate with h as some function of t. You could call it, I don't know, any constant c, and then know that the derivative of a constant is 0. dh dt is equal to the derivative of the constant is 0. But it's not necessary. You could just, instead of thinking of h as a function of t, you could just think of it as a constant, and that makes differentiating a lot easier. Now, x is changing with respect to time, and so is theta. So this is theta right here, right? Here's theta, and it's changing. It's going to get larger, smaller, depending upon whether x is increasing. I don't even know. X could be increasing. The height is staying the same. So theta could be getting smaller. So these could be different time periods, right? And it's different x values that you're going to have along the base of this right triangle. So theta could be getting smaller or larger as x gets smaller or larger, depending, right? Okay, the angle theta measured in radians is defined by this relationship. And it's just basically that if this is x, this is h, tan theta equals h over x. Now, you want to find a relationship between the rate at which theta is changing with respect to time and the rate at which x is changing with respect to time. Now, the way to do that is literally to just differentiate this relationship. So you have it that tan of theta is equal to h over x. Now, h over x is the same thing as h times x to the negative 1. Now, I wrote it like this because I want to illustrate that h is a constant, so I could just take it out, okay? If I didn't think of h as a constant, then I would need to do quotient rule on this and remember that dht will be 0. But to me, that's more work. I don't want to do more work, so I'm going to do that h is a constant. It's just h times x to the negative 1. And I'm going to differentiate both sides of this with respect to time. So the derivative of tan theta, remember, theta is going to be changing with respect to time. Theta t is some function that is changing, right? So there's going to be some d theta dt. Okay, this angle is changing as time progresses. So remember that this is some function on the inside with respect to time. So knowing that, I got to use chain rule. So the derivative of tan theta is secant squared theta times d theta dt. The derivative of the inside, right? This is the inner one, theta. And the derivative of tan is secant squared times the inner times the derivative of the inner, d theta dt. That's chain rule. Now, h times, and remember, x is also a function of time. So I got to do chain rule again here. This is x to the negative 1, right? So it becomes negative 1 times x, but now this goes to the negative 2 times dx dt, the derivative of x with respect to time. And now you get a nice little relationship for d theta dt. So this is going to be, when all is said and done, I'm going to have negative h over x squared and dx dt times dx dt over here, right? X squared on the bottom, and when I divide by secant squared theta, I have secant squared theta over here, is d theta dt, and I'm on my way. Because remember, I wanted to find the relationship between d theta dt and with respect to time and dx dt. So I have d theta dt now. Now this is weird. Why is there secant squared? There's no secant squared theta here. But I do know tan theta is equal to h over x, or I know my triangle looks something like this. I can solve for this missing side, x squared plus h squared square root. And if I'm careful, I can see secant theta as equal to the square root of x squared plus h squared over x. That's the definition of secant. And if I square this, I get that instead of writing secant squared theta, I can write x squared plus h squared over x squared. And now I have my relationship for d theta dt. And now I got negative h x squared times, and instead of writing secant squared theta, I write this. So x squared plus h squared over x squared. And these things now cancel, and I'm left with just the dx dt over here. This gives me d theta dt as equal to negative h over x squared plus h squared dx dt. And that is choice A, negative h x squared plus h squared dx dt.